All right, so now let's look at hypothesis testing for one sample mean, and actually it's hypothesis testing for a population mean. My apologies. So if we're looking to estimate the probability of obtaining our sample mean or a result more extreme, we will conduct a one sample t-test. Now, again, we're going to use our state plan do conclude, where our state will be our parameter and our hypothesis. Well, now mu is the true population mean. Next, in the plan step, we'll look at our assumptions and the name. And again, random, independent, and normal because the population is normal, the central limit theorem applies, or our graphical display reveals no extreme skewness or outliers. If these conditions are met, we'll use a one sample t-test for a mean. Well, our test statistic and our p-value will be in our do step, and we are going to now start using a TCDF function in the calculator, which of course I'll show you how. And again, we have our sample minus our mean over our standard error. So we'll get these from the text of the problem, and then here we've got our p-values, and again, these are one-sided tests if it's less than or explicitly greater than, whereas here we have our two-sided test, which we'll do some examples in class. Now in our conclude, if the p is low, we reject the hoe. There is sufficient evidence to claim, blah, 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 blah. Or if the p is high, we cannot deny. We fail to reject the null hypothesis since there is not sufficient evidence to claim. So we'll still keep our state plan do conclude examples here. So let's take a look here at teacher salaries. A state study on labor reported that 1/3 of full-time teachers in the state also worked part-time at another job. For those teachers, the average number of hours worked per week at the part-time job was 13. After an increase in the state teacher salaries, a random sample of 400 teachers who worked part-time at another job was selected. The average number of hours worked per week at the part-time job for the teachers in the sample was 12.5 with standard deviation of 6.5 hours. Is there convincing statistical evidence at the level of alpha as 0.05 that the average number of hours worked decreased after the salary increased? A lot going on there, but let's start with what we know. In our state, we want to test the null hypothesis that mu is equal to 13 hours. And we're going to test this against the null hypothesis that our number of hours decreased after the salary increase. And I know the decrease increase back to back can get a little confusing. But remember, I'm trying to figure out that the number of hours worked decreased, not the salary. Well, what do these symbols mean? Well, here, mu is going to equal the true mean number of hours worked after the salary increase. Now, in my plan step, I was told I had a random sample of 400 teachers with a sample average of 12.5 and a standard deviation of 6.5. So I meet the condition that I have a random sample, so I can generalize. It is reasonable to assume there's at least 4,000 teachers in the population of teachers in this state, which is good. So sampling without replacement is fine. The degree of dependence is negligible. My sample is independent within itself. And lastly, the normal model will be appropriate by the CLT since 400 is greater than or equal to size 30, meaning that my sampling distribution of X bar is approximately normal, and I can use this for calculations on my p-value and test statistic. Well, since these conditions are met, I will use a one sample t-test for a population mean. Again, only one sample. It's quantitative. I'm finding evidence, and I'm doing this for mu. Okay, now we go into our do step. And in the do step, we're going to add the degrees of freedom, n minus 1 here. So 400 minus 1 is 399. And using my formula here for my test statistic, I get negative 1.5385. Well, to find the p-value, since I want that it's less than, I want the probability that t is less than negative 1.5385. Now here, notice that I'm using the calculator, so I have to label what inputs I'm using. Well, a lower bound of some very large negative number, an upper bound of this test statistic, here's my degrees of freedom. And so let's take a look at where this happens in the calculator. So again, you're going to go here to calculate. You are going to hit menu, statistics, and we're going to go to distributions. Well, now we're using a TCDF model. So here, you can just type in negative 9999999, something like that, a very large negative number. The upper bound was our test statistic of negative 1.5385, and our degrees of freedom was 399. And when I do that, I get a probability of about 0.0624, which is what I believe I wrote here, 0.0623. Now, you might be slightly confused to where this is coming from. So I'm going to look at my good friend here, StatsMedic. And when I go to the resource and applets page here, they have a t-distribution. So right here under normal distributions and probability, well, we said that we had 399 degrees of freedom. So this is what our t-curve would look like. And you can, oh, sorry, 399. Okay, I want 399. Come on, 300. Okay, it's just not working with me. So, all good. Let's refresh this really quickly. So our t-distributions, we want 399. Plot the distribution. Okay, it's not going to work. All good. Well, notice that when I plot, and again, it just rounds down because 399, 300 on our t-chart. Well, when I try to approximate it with a normal model, you can hardly see it, but this purple outline that's showing up here, 300 is a large amount of degrees of freedom, so this closely approximates a normal model. Well, I want to find the area to the left, because it's a less than, of negative 1.5385. And when we calculate that area, notice 6.25% is about 0.0625. So assuming this t-curve here, the probability when we standardize our test statistic, our sample mean, it's negative 1.5385. It falls that many standard deviations below the mean here. So this is our p-value. This is the probability of obtaining our test statistic or more extreme. So that's what we're doing in hypothesis testing, is we're finding this value here. So I plotted it and I get about 0.0625. So that is where this comes from. So I found the calculations on my calculator using the tcdf function. And 2, we can see here that our t-distribution confirms that. All right, well, since our p-value of 0.0623 is greater than our alpha value of 0.05, we fail to reject the null hypothesis, and that is because we do not have sufficient evidence to claim that the true mean number of hours worked at a part-time job decreased after the salary increase. Now, I'm going to commit a cardinal sin here, and I'm going to show you a quick calculator command to check your work. So if we go here to menu, and we do statistics, and we go to a stat test, I want a t-test. I don't have the full data, I just have some statistics here. Well, the claim is that we worked 13 hours. Our sample mean was 12.5 with 6.5 standard deviation, and our sample size was that of 400, and we're testing that we've had a decrease. So this is how we do this in the calculator. And it looks, my degrees of freedom is about 399. Even doing the work by hand, we get the same test statistic and about the same p-value. So while the calculator is effective in shortening the work, your doing this by hand is going to be so essential to your understanding. But of course, I'm not evil. You can always check your work as needed. So that is just the connection here of all the different elements. I plot my t-distribution. Here's my p-value, my sample mean. I can do the calculations here in the calculator. And then we make a conclusion based on this value. Well, there's always a follow-up question. So here, since we failed to reject the null hypothesis, we committed a type 2 error. So that would be the error associated with our decision. But here, it says describe a type 1 error. So even though we didn't necessarily commit a type 1 error, you still need to have fluency in being able to describe the type 1 error, the type 2 error, and the power of the test. And don't worry, because of course we will review this in the next lesson. Well, a type 1 error is when we reject the null hypothesis, but the null is false. So here, we claim that the true mean number of hours worked decreased from the 13 hours, when in reality, the numbers of hours did not decrease. So what we did here is we rejected the null hypothesis. We claimed this, but the null was actually true. So we claimed it was less than 13, but in reality, it hadn't changed from 13. So that's just an idea there of describing the types of errors. Well, let's take a look, and this is also another popular AP exam question, is, look, what if I give you the null and the alternative hypothesis, and I give you a sample size, and I give you a test statistic? Can you figure out how to find the p-value? And I would have asked you to pause, but I wanted to ruin your fun. So here we look, and my mean is centered at 0. I have a sample size of 7, so my degrees of freedom is 6, and I have a t-value of 1.935. So if I go here, and let's go ahead and change this to 6 degrees of freedom, and I plot the curve here, I want the area, and I look at my null hypothesis, it's greater than, so I want the area greater than 1.935. So we want the value to the right of 1.935. And so if I plot that, it's about 0.0506. that's basically what we did here is we formed this t-curve, and even using the calculator command or plotting it, I get the same p-value. Well, if the p-value is greater than the alpha level, we would reject the null hypothesis here. So here we would reject the claim that the mu is 0 in favor that the mu might be greater than 0. All right, so now I want you to pause the video and take a look at some conditions here. So the next two examples, you're interpreting the p-value, you're using the p-value to make conclusions, and you're also just verifying your conditions for inference. So I'm going to pause the video here. I want you to take about 2 minutes to try these out on your own. All right, so hopefully not too challenging. We see in this situation that I took a convenience sample, and that's of the first 35 students who entered the hallway. Now, it's a convenience sample, so I can only generalize my results to those students. It won't do me any solids here in having the ability to generalize to the population. Well, the other conditions are met because 35 is less than or equal to 10% of 4,000 students, and 35 is sufficiently large sample size to apply the central limit theorem. Thus, the sampling distribution of the sample means is approximately normal. In this example down here, we are asked to interpret the p-value and then state a conclusion, and the p-value just sounds a little something like, assuming the null hypothesis is true. So assuming the true mean salary of graduates is $45,000 and $45,327, the probability of obtaining our sample mean, or our sample statistic, or more extreme, is 0.045 by chance alone. Now that is a really small probability, so we would call this statistically significant. Now, since the p-value was less than the alpha level, we're going to reject the null hypothesis because there is sufficient evidence to claim that the true mean salary might be greater than this claimed value. Well, there you have it, folks. That is a little bit more information on a one-sample t-test for a population mean. Now we're going to review errors, and we're going to talk about a special type of t-test, specifically a paired t-test. So stay tuned to learn a little bit more about confidence intervals and hypothesis testing or paired t-procedures.